For this one, you need to state Faraday's law of electromagnetic induction. So again, refer back to the equation, and then you can try and turn it into words. So we refer to epsilon as the induced EMF, and then we can change Lenz's law into a proportional sign, so that the induced EMF is directly or proportional, and then because it's divided by time, we can say rate to the rate and then of change we've got a delta sign, and then n phi magnetic flux linkage, so rate of change of magnetic flux linkage. Figure 5.1 shows a magnet being moved towards the centre of a flat coil. A current is induced in the coil. Use ideas about energy conservation to state and explain the polarity of the face of the coil nearer the magnet. So we should be aware that if we are going to induce electricity or induce a current, then we need to do work. So in which case we need to, because we've got a north pole here, we need to induce a north pole just there. It's a repulsive force. So by doing work against two north poles, you are doing work against the repulsive force, and that is what gets transferred into electrical energy in the coil. Now, although I've written quite a lot for this one, it is only 1 mark, and the 1 mark was for stating North Pole, but I think it's important that you've at least had a chance to read through the reasons if you are unsure. So press pause if you need to, otherwise I'll move on. Figure 5.2 shows the magnetic field from the North Pole of a vertically held bar magnet devanche. A small flat coil is placed at A. The coil is moved downwards from position A to position B. The plane of the coil remains horizontal between these two positions. Explain why there is no induced EMF across the ends of the coil. So for this, it's really important that we zoom in on the part that we're looking at. Now what we can see is, to start with, through the coil, there are 3 lines of flux. At the end, there are 3 lines of flux. Now, you're asked to explain why there's no induced EMF across the ends of the coil. Well, there's no change in flux density. We've got the same number of lines of flux cutting through at the start as we do at the end. So how you would write that is there is no change in flux or magnetic flux. And you can use the word linkage because it's a coil. So that means there's no change in magnetic flux density as well. But do not talk about strength. It's all going to be about magnetic flux linkage. In figure 5.3, there's a graph showing how the magnetic flux density B varies along the horizontal line XY in figure 2, so from the previous one. The same flat coil from I is moved at a constant speed from X to Y. The plane of the coil remains horizontal between X and Y. On the axis provided in figure 4, sketch a graph to show the variation of the induced EMF E across the ends of the coil with distance from X. So, reminder, look at your axes, and you should remember that magnetic flux density and EMF, you can use Faraday's law, so that's the same as that, so it's the rate of change that we're looking for. So because there is no change here, here, and here it's continually 0, that means you're going to get no EMF at that point. So 0 to 3, 5 to 8, and 10 to 12. However, there is a change in flux density there and there, and what we need to realise is they're going in opposite directions. So in the diagram below, we're going to need to have 2 pulses where B is changing, and because they're in opposite directions, they need to have opposite signs. So something like that would be absolutely fine.